LRO was launched on June 18, 2009 from Cape Canaveral, Florida. It took 4 days to reach the moon and then was inserted into a polar orbit. The orbit was gradually lowered to the point where it's now in its mapping configuration, where it flies from pole to pole around the moon, one orbit every approximately 2 hours. The typical altitude of the Lunar Reconnaissance Orbiter orbit is about 50 kilometers above the surface, which is very, very close, given that the radius of the moon is about 1,700 kilometers. So it's just really skimming right above the surface of the moon. And Diviner takes data continuously throughout the entire course of the LRO mission. So the Diviner instrument generates data. It's sent through the telemetry system on the spacecraft back down to Earth and received by ground stations. We take the raw digital feed from the instrument and then turn those numbers into calibrated numbers where instead of just talking about them as ones and zeros, they're turned into actual numbers that represent, for instance, the temperature of the lunar surface. You can think of each of the Diviner individual temperature measurements as a small tile on a giant global mosaic, which contains millions or even billions of actual tiles. These data are all assembled in a computer and then ultimately projected in 3 dimensions to make a gigantic picture of the global temperature field of the moon. One of the major challenges for the Diviner science team is to make a physical model of what Diviner is actually seeing on the surface of the moon. The models we create for Diviner are sort of analogous to a video game, but instead of like modeling a character or a scene that you might be playing with on your computer, instead the scene is the moon itself and the quantity of interest is its temperature. We know from looking at the Apollo samples that there's a great variation in terms of the materials you might actually see on the surface of the moon. There's very fine soil. The soil is even finest right at the surface and then becomes more compacted as you go down. There's also rocks on the surface of the moon. And the Diviner temperatures that we measure are sensitive to the properties of all of these things. What we do in our models is adjust the thermal properties of soils and rocks until we get a good match for the Diviner data in all the different channels. And then once this occurs, then we can then use the Diviner data to tell us something more or less directly about the nature of the surface materials on the planet, and then create maps that are best fits to our Diviner data. Modeling the moon is particularly challenging because of the fact that the moon is really not a featureless sphere. The moon has very high mountains, as high as Mount Everest, very deep valleys, as deep as the deepest trenches in the Earth's oceans. And in some cases, these major features are found in close proximity to each other. The moon also is very rough. When you look at the topographic relief, it's rough on many scales, all the way from kilometers all the way down to microns. The surface of the moon is very rough. And any realistic model you have of the moon has to properly take into account its detailed shape. We've been working very hard to incorporate data from various types of instruments into a digital moon model, which attempts to represent the true shape of the moon on various scales. And through this virtual representation of the moon, this is how we're able to make detailed models that realistically portray the Diviner data and help us infer and extract the maximum information from the Diviner data set.